The next concept up on the table is that of electric power. Much like in kinematics, we said power was equal to how much work you did divided by time, which really we also know that the work is going to be equal to the charge multiplied by VAB. Divide this guy by time, and we can kind of say, hey, wait a second, this guy right here, charge per time, I know that current is going to be the charge per time. So I can say that my power transformed is going to be equal to my current times my voltage. And much like in the case of kinematics, the unit is going to be a joule per second or a watt. And we can still say that the unit is going to be a watt. And we can say, hey, as long as the device obeys Ohm's law, this is going to be my main equation, but I can do substitutions for V, say V is equal to IR, or I could substitute in for current, that current is going to be V divided by R, and I can come up with two alternative equations for ohmic devices only. And really, you could use either one of these equations. Suppose you're given a problem and you're given, say, just the voltage and the resistance, you could go ahead and calculate a current without having to work your way through Ohm's law. So let's start to get into household circuitry, and let's start by talking about electrical power that you read off of your power bill. What you're actually paying for is not going to be power, but it's actually going to be energy. So the power consumed multiplied by time. Now we've been pretty much talking in joules, but the power company is going to be measuring it in kilowatt hours. Essentially you can kind of say, hey, 1 kilowatt is 1,000 watts, and 1 hour is 3,600 seconds. So I can say I have 1,000 watts multiplied by 3,600 seconds. So 1 kilowatt hour is actually 3 times 10 to the 6 joules. So quite a large amount of energy here. And very typically we're not going to be using 1 or 2 kilowatt hours to power a house for a month. We're talking a couple hundred. So we're talking quite a bit of energy here. Now, thinking a little bit more about household circuits, we know that we have wires in our house, and they're actually fairly low resistance, depending more or less on the gauge of the wire, thinking back to the equation for resistance, length, and area. However, if you think about the power that's eaten up by the wires in your house, it's actually pretty small, but it's going to depend on the current and the voltage. Or we could also say that this is going to be I squared multiplied by R. So R is going to be what it is. It's going to depend on the wires, but if the current is high enough, then essentially the wires can become hot enough to start a fire. Now that's actually a bad thing. So we use these things called fuses or circuit breakers, which is essentially going to say, hey, this wire right here, I'm going to put this wire into my circuit. So put some power source across this guy, and we're going to get current flowing through this wire. This wire in the fuse is going to melt once the current reaches some predetermined value, and once this chunk of the wire actually melts, then it breaks the circuit and current won't flow, melting the wires in our house that we don't want to catch on fire. Now kind of the old-timey way to do this is to use fuses, where you'd say, hey, I'm going to hook this guy up past my power source, and once this current reaches, say, 1 amp, then this wire is going to melt and it's going to break my circuit. This one's a little bit thicker, so let's just say that this one's a 5 amp circuit, and then this one might melt at, say, 20 amps. Now the bad thing about a fuse is if once they have been burnt out, then the fuse is destroyed and you need to actually replace it. And so nowadays we have circuit breakers, which are much more common than they used to be, and really these are just switches that are going to open if the current gets too high. So we kind of have a bimetallic strip here. Remember I yammered on about that in chapter 13. Here we can actually see a use for one, where current is going to flow through it. It's going to get hot. Once it heats up past a certain point, it's going to bend, opening up this contact and making the circuit an open circuit such that current can't flow through it. Now, the other thing about household voltage is that it's going to be alternating current. And what that kind of means is if we consider just the current flowing through a battery, or a current from a battery, it's going to flow steadily in one direction, and we would call this direct current, or DC current. So if we were to plot the current versus time, then we just say, it's going to be, 5 amps for all eternity. With AC power, the current's going to vary sinusoidally. So you can kind of say, hey, let me look at my current, and as a function of time, it's going to behave like a sine function. Kind of, if I wanted to take a look at this take a look at this. Here I've set up a circuit where I have a light bulb right here, and I'm going to first light it up with a battery, and the battery is going to cause these little blue guys, these electrons, to flow through it and light up the light bulb. Now if I were to say, hey, what if I were to connect this guy up to an AC power source? The AC power source is just going to slosh charge back and forth through this light bulb. Because these charge is still moving through the light bulb, it's still going to light it up. You can even kind of see that the current here is going to go up and down more or less sinusoidally. Now you can see that there's regions where the electrons are totally stopped and they're not moving. In this case, the current's equal to 0 and the light bulb's not lit up. What this kind of means is, there's periods where our lights are not lit up in our room. So we tend to operate our house is at 120 volts AC, and then the frequency of oscillation is actually going to be equal to 60 hertz. Because it's happening 60 times per second, we can't actually perceive it with our naked eyes, but it is actually true. Now, if we wanted to actually write this down using equations, I'm not going to really grill you on this, but we could say that both of our current and our voltage, they're going to vary sinusoidally with the frequency. Now remember that angular frequency is going to be 2 pi multiplied by the regular frequency. So we can say, hey, our voltage is going to be some initial voltage, some maximum voltage actually, multiplied by sine omega times t, and the same is going to be true for current. If we wanted to talk about power in an AC circuit, well, power is going to be current squared multiplied by resistance. And so if we take that current from the last slide and plug it in right here, we're going to get I naught squared resistance and then kind of that sine squared. Keep in mind that sine squared omega t is also going to be sine omega t quantity squared, just in case you ever have to plug that guy into your calculator. Now with AC circuits, we tend to pay more attention to average power, so I put a little bar over there, that means average. That's actually going to be the average current squared multiplied by the resistance. And you can kind of convince yourself that this current is going to spend an equal amount of time over here and an equal amount of time over there. So really the average power is just going to be 1/2 of this initial current squared multiplied by resistance. So once again, we're typically interested in the average power, got a little ahead of myself there, which is just going to be 1/2 of the current squared multiplied by the resistance. And again, this is for AC only for both of these two guys. Now, if we wanted to think about alternating current in a household, we know that it's going to go up and down, essentially circled around 0. So the current's actually going to have an average value of 0. So when we're dealing with household circuits, what we do is, first thing we do is we take the current and we square it. That's going to essentially pull all the negatives up here to be positives, and then of course we have to square the magnitudes. And then we take the average, and then we take the square root of that. That's going to yield us something called the root mean square. See, we're taking the square root of the mean of a square. And this value actually tends to be about the initial current divided by the square root of 2. And what we can essentially do is, this is the value that we can use with Ohm's law for alternating currents. We just have to keep in the back of our heads that it's about 0.707 multiplied by the initial current and the initial voltage. Now, one important thing about electric current is these electrons are moving around inside of the wire, but the electron is not going to, say, run from over here to over here producing the current. Electrons in a wire that's not connected is actually just going to be kind of bouncing around and taking a random walk, as we call it, simply because it has some temperature associated with it, and it's actually traveling at a very, very large speed. If we were to apply a potential difference and get an electric field in there, then this electron is going to now move. It's still going to be kind of bouncing around. It's going to take this weird looking jagged path. What we kind of call this is, we say that the electron is moving with some drift velocity, and actually the drift velocity is actually going to turn out to be quite small. This equation right here gives you a method to calculate what the drift velocity is. Suppose you know what the current is. Suppose you know what the number of electrons are. Suppose you know what the charge of an electron is. and suppose you know the area of the wire, then we could go ahead and calculate out what that drift velocity is. And actually, for typical currents in the 10 to a couple hundred amp range, we're talking about like 10 to the minus fourth meters per second. What that really says is electrons themselves are not moving from one side of the wire to the other. They're just kind of like football players passing the ball around. So if I've got a wire right here and I want to have some current flowing through it, these electrons are kind of drifting more or less in that direction right there. And well, actually they'd be going, in that case current's going in this direction, but they're kind of just passing the charge from one electron to the next electron to the next electron to the next electron, working their way down the wire.